Hello and welcome to a new How to Code a Game Like Minecraft in Unity video. Sorry for the delay, it has been quite a while, probably the longest time I've gone without a video since I started this whole thing. A few things to start off with, a brief mention to load distance. A few of you have noticed that we are not doing anything with our load distance at runtime, we're just doing it at the start. Well, actually we're not doing it at the start, that's another thing that at least one person's noticed. But we're not doing like a check view distance kind of thing for the load distance. I didn't want to cover that in the last video because well, to be honest, it was a very long video, and two, it's basically identical to how we do check view distance, and I'm trying not to just repeat myself over and over again. I may cover it at some point because we may do something a bit different with it if I can think of a different way of doing it. But if you want to get the load distance up and running, just basically copy your check view distance and substitute check view distance with load distance, and obviously create all the new queues and things like that. With regards to load distance, the error for this week, because we can't start one of my videos without fixing an error from a previous video, is if we go into our world script, we didn't actually use load world. We went to the trouble of writing this function here, but we didn't use it. So let's just go up to here, and just before we call generate world, actually we'll go there. We just want to call that. So the next thing, well, actually, first we're going to move this, although it's a bit irrelevant for what we're going to do next, but we'll just put that there because we don't want threading to start. We don't want the update thread to start running before we've finished initializing the world and everything. But it's not going to make a difference for this video because we're going to disable threading. A lot of what we're doing in this video causes all sorts of problems with threading, and it's already going to be a long video again. So I'm trying to keep this focused just on the lighting. So for now, we're just going to disable it, and we may fix it in a future video. Basically, I looked at the Unity job system and decided that it wouldn't work for this project, but I've been told over and over again that it should work for this project. So I'm going to revisit it, and maybe we'll use Unity job system. Maybe I misread it the first time, or maybe it's moved along since then. I think it was about a year ago when I first looked at it. So for the meantime, rather than open the menu, I'm just going to go straight into the settings folder, and I'm going to set that to false. So next up, we're going to make a little change to the way that we create chunks. Right now, we add chunks to this create chunks queue that we've got going on, and then we make them at runtime. We check the create chunks queue, see if there is one, and we create them if there is. The reason we did this is because creating chunks had quite a bit of overhead to it. We had to populate the voxel map and then draw the chunk later. We don't need to do that anymore because we're doing the load world thing. So we're loading all the data beforehand, and by the time we actually come to create a chunk, everything is ready to go. So we don't need to create the chunks separately. The way we're going to fix that, sorry, I've just realized I've been talking into the wrong side of the mic for the first 10 minutes of this video. So the way we're going to do that is, wow, that sounds different. So the way we're going to do that is if we go into our scripts and we open our world script again, and we have somewhere up here, we have a create chunks queue, or chunks to create up here, just delete it. And that's going to give us all sorts of errors. So let's go tackle these one by one. So this we can get rid of entirely. We're not going to be using that at all. What have we got next? I think this one down here. Nope, not that one. There's another one that we can just delete. Oh yeah, the create chunks function we can get rid of entirely. This one we can also delete, and you'll see why that will work in a second. And then this final one down here, this wants to get changed quite a bit. So what we're going to do now is, first off, we still want to check if it's active, and then we create a new one like this, but we're not going to add it to that, and we're not doing this else if check anymore. We're just going to say set it to active, because the check isn't really necessary, because it's two operations. We're saying if it's not active, set it to true, whereas if we just set it to true, then that's just one operation. If it's already true, it's not doing anything, and if it isn't true, it's setting it to true. Either way, it's one operation. We don't have that if statement check. So we'll just get rid of that entirely. Now, if we go and grab our chunk script, which is in here somewhere, we don't need the separate init and constructor anymore, because we don't need to put off initializing the chunk until we're ready. We can just do it as soon as we create the chunk. So basically just delete these two lines here, and then that makes all of that part of the constructor. And so what that means is that now when we do this, all of this is run. And same for generate world, wherever that was. This code could do with some serious cleaning. Same here. Now, when it initializes this new chunk, all of this code here gets run automatically. And because we're no longer populating the voxel map in this code, this constructor isn't nearly as expensive as it used to be. Now, the next change, going back to generate world actually, is that we no longer need generate world. Because we're loading all the data in advance, and we've already loaded the world, and then we've got check view distance doing all the heavy lifting, there's no point in having this anymore. So if we just yank these two lines out, and then we can just delete this. And then we just want to put those 2 lines back where we called generate world. So that's all the preparation. Now we need to get to the lighting. So first thing we're going to do, just because it gets asked for a lot, even though it's a very simple thing to do, and it will help us see the lighting working better, is we're going to create some caves. And this is next to nothing. I do keep telling people it's not hard to do. But if we go into our assets, into our data, into our biomes, just highlight all of the biomes and then go to the loads, add an extra load, and just call it caves. And then I've messed around with the details a bit to come up with some values that look nice enough for me. So the block ID needs to be 0 to make it into an air block. Minimum height 5, maximum height 60, scale 0.1, threshold 0.55, and then your noise offset, just type in some random number. That's fine. So that gives us caves. If I run that now, we should find we have caves. And there we go, we have caves. And we can see one of the many problems with the current lighting system is whatever's going on there. We're kind of getting light bleed through from the top, but don't worry, all that will be fixed by the end of this video. Okay, another thing that I forgot to mention, actually, the save game data, if at any point you start getting weird errors through this video, it's probably because the save game data is conflicting with the things that we're doing in this video. So there's a good chance that if you get weird errors to do with serialization during this video, all you need to do is delete your save game data, which should be in my case, it is in users, my username, app data, local low, Beegs, how to code a game like Minecraft in Unity, and then testing here is the name of the world that we've been creating. So if you get any weird serialization errors, just delete that folder and it should be fine. So the first step we're going to take is we need to change the way that we store light, because right now we have, if we go to world and we go to block types down here, we have this float for transparency. That works fine for Unity, but I did want to try and make this as much like Minecraft as possible. So, I mean, you can see how it works as a float, but we're going to make it work as a byte like Minecraft does. So 0 to 15 rather than 0 to 1. So the first thing we're going to do is go back into worlds and drop to the bottom, and we should find our bytes somewhere, block types. There they are. And we're just going to change this from a float transparency to a byte opacity. So before, the way that this worked was it was kind of the amount of light that can carry on past the block. Now we're going to change it so that it's the amount of light that is stopped by this block. For example, for a stone block, this value will be 15. The maximum amount of light you can have, this block will stop it all. Whereas for a glass block, it will be 0 because it doesn't stop any light. And then for a leaves block, I'm not sure what Minecraft actually has it set at. I think I've been settling on leaving it as like 3 or something. We should have an error in chunks, I think. Yeah, here. So the way we're going to fix this error is we're going to delete this entire function, because we're going to be redoing the way this works entirely. Then just delete that call to it, and that should be all we need to do to fix the errors for that. So then if we go back into Unity and we pull up our blocks, we can see we have this opacity value. Air just wants to stay as 0 because it doesn't block anything. But then all of these, bedrock, stone, all want to be 15. Glass wants to be 0, obviously. We don't want glass blocking any light. And leaves want to be, I'm gonna put it at 3 because I think it shows up more. I think Minecraft has it at 1. Actually, you know what? I'm gonna put it at 5, just so we can see it clearly. We don't want really faint shadows when we're just trying to make sure it's working. Again, you can play with these values and set them up what you want. And obviously cacti and cactus tops stop light. So that's that updated to the new system. So our next thing that we're gonna do is we want to be in world. We're going to create a function for adding to, we'll just find it somewhere. We're going to create a function for adding to the chunks to update list. And the reason we're going to create a function is because we want it to check to make sure that the current chunk, the chunk that we're trying to add isn't already in the update list when we add it. So we'll just stick it down here by update chunks. And we'll have two ways of adding it. So the first one is just going to be public void add to update. And that's going to take in just a chunk. And that's going to call the second version of it that we're going to write in a second, add chunk to update. And that version is going to take in a bool. And that bool is for, if you remember, we have in chunk, in edit voxel, we have insert here because we're trying to put we want this chunk to be top of the list because it's just been edited. So it needs to be updated before anything else, because it doesn't matter if a chunk off in the distance that's just been loaded into the world takes its time. But a chunk that a player has just modified right in front of you, that one needs to be updated quickly. So this bool here is to tell the function that we're about to create that it needs inserting to the top of the list. Whereas if we just call add chunk to update without putting the insert true there, then it will just stick it in the list wherever. So the other version of it is going to be public void add chunk to update. And this one's going to take in a chunk and a bool insert. And then obviously we want to lock this, although again, this may be all irrelevant. It's irrelevant for this video because threading's turned off, but it may be irrelevant in the long run, depending on if we do move to Unity jobs. So the first thing we want to do is, after the locking obviously, is to make sure that the chunks to update does not contain the chunk that we are trying to add. Because if it does, we don't want to add it again, because then the chunk will be updated twice, which takes up more processor time. Then we'll say if insert is true, chunks to update dot insert 0 chunk. So if we pass that value in as true, it will stick this chunk that we're trying to add to the update list at the very top. And then else just stick it in the list as normal. Now, in order to figure out where we need to update to this new function, one way we can easily find everything is to just go up to where we've got our chunks to update list and make it private. And that will immediately create errors here where we try to add to the chunks to update list. So let's go find those. So that's the other advantage of this, is that now that because we've put the lock in here, then we don't need to worry about locking it from wherever we call it. So right now we're locking it there. We don't need to do that anymore. We can just call the function. Now, instead of adding it to the chunks to update list, we say add to chunk update this. And then down here somewhere, we should have 2 more of these. And this is exactly the same, except now we're going to use the bool to tell it that we need this one inserting to the top of the list. Add to chunks to update, chunks, true. So that one will end up at the top of the list. And then same again for this. Help if I spell the function name right. Add chunk to update. And this one wants to be this, not chunks. Okay. So some other stuff that we're going to need in order to make this lighting system work. At the minute, when we want to get hold of block properties, we do this big thing where we say world instance, block types, neighbor ID, and then etc. Like, that's a bit over the top. And we have a way of doing it where we don't need to do that anymore. So let's go into our scripts folder and pull up our... Oh, did I save that in chunk? Sorry. Yep, sorry, it's down here. We are going to put that in a separate file, that's why I got confused, but for now it's in the chunks folder. So we're going to create a public block type, which we'll just call properties, and it's going to be a get value. We'll say get return world.instance, and remember we made the world a singleton pattern, so we can just access it from anywhere using world.instance. And then we get block types, and we pass in the ID of this particular voxel. And now instead of typing all of this, we can just... I'll just grab the name there. We can just say neighbor.properties. And same for here. In fact, what we'll do here is instead of this block ID thing here, we'll say voxel state voxel equals, and then down here we can just simply replace this with voxel.properties. And if we just do a quick search for any other instance of block types, okay, so that's all of them. So now, without storing any additional data in the voxel state class, we have a way of instantly accessing all the variables related to the block that is in that voxel state. Now, we do need our light to work a bit more like Minecraft's light if we're going to use bytes instead of floats. Go back in here and we need to open our voxel data class, and we need a way of converting our bytes value that we're now storing into floats that our shader uses to draw the light. So we'll do that by creating a public static float unit of light, and then it's going to be a get value, get return 1f divided by 16f, because there are 16 levels of light, not to 15. When you get into serious optimization, you could look at storing this value as it is, like the actual result of 1 divided by 16, rather than the equation or the sum, because this is a calculation, which is slightly more expensive than just pulling a number out of memory. For now, I just want to leave it like this because you can quite clearly see what it is that we're doing. We can delete the light fall off value because now our fall off is just 1 light unit, so we don't need this anymore. And then now we're going to go back to voxel state, and we're going to rework these light values. So this is no longer going to be a global light percentage. This is going to become a private byte light, and then we're going to have a public byte, which is light without the underscore, and this one's going to be a get setter, and the get will just return... This is going to get more complicated, obviously, but for now, let's get everything set up. The get is just going to return the light value, and the set is going to set the light value. Typing is on point, as always. And then down in here, we're just going to say light equals naught. Oh, actually, sorry, no, we're going to delete this one. We don't need... Right, so we're never going to need a empty constructor for a voxel state. If we're creating a voxel state, it needs to have a voxel in it. So we get rid of that because we don't want the temptation there to be able to create an empty voxel state. So here we're going to say light equals 0. And then also we're going to create another value, which is called public float light as float. And this is another get, and it's just going to return float light. So we're recasting our light value, which should be 0 to 15 as a float, and then multiplying it by voxel data dot unit of light. So if you remember, voxel data unit of light is 1 divided by 16. Our shader takes in a value between 0 and 1 for the light. This takes in a value that is between 0 and 15 and multiplies it by essentially what 1 divided by 16 is to get us our light value as a float, which we can then pass directly into our shader. So if we go back up here, we should have an error, and we can just replace this by light as float, and that should get all that back to as it was. If we run this now, we should find that other than having completely broken the lighting system, everything is more or less the same. Everything still works the way it did before. All the changes we made haven't really affected the game, other than we deleted the calculate light code, so now we have no lighting. But obviously that's what this video is about, so we'll get back to that. So we're going to create a new script to handle our lighting code, which we'll just call lighting. We delete all this. It's going to be a public static like our voxel state one. And so our first function that we're going to create here is the light casting function. Basically the first part of the cast natural light function that we just deleted, the bit that just casts a ray of light straight down in one column of voxels and sets the lights for just that column. So that's going to be the first thing we do. So it's going to be public static void cast natural light, and we are distinguishing between normal light and natural light here because obviously sunlight will propagate all the way downwards until it hits a block, and then it stops completely and light propagation takes over, whereas block light just emits from that one place and fades out. This is going to take in a chunk data, an X position, an Z position, and a start Y position. So what this is we obviously, when we're doing a new chunk and we're working out all the light, we want to be casting from the very top of the chunk to the very bottom of the chunk. However, if we modify a voxel, say at block 32, nothing above that voxel is going to be changed as far as natural light is concerned. So we don't need to redo the light from that point. We only need to work it out again from that point downwards. So this start Y position, oh, sorry, I need to actually give that chunk data a name. So that start Y position is basically, we're telling it where to start from. When we're doing a new chunk, that where we're starting from is going to be the very top of the chunk, but it's not always going to be that. When we modify a voxel, we only want to start from where that voxel is. So we're going to do a little check here just to make sure that we aren't passing in a value that will cause an error. So if voxel data.chunk, or if start Y is greater than voxel data.chunk height minus 1, because we're starting from the array, which goes from 0 to 1 less than the actual chunk height, then we're going to say start Y equals voxel data.chunk height minus 1, and then we're also going to put up a little debug warning. Debug.log warning. We'll just say attempted to cast natural light from above world. No bracket there. So let's get into the actual code. As far as I understand it, the way Minecraft Sunlight works is it will propagate forever until it hits a block, even if it's a transparent block. So I think the way I did it before is I had the transparency, or the transparent blocks, shave intensity off the light. So if a block blocked half the light, then the sunlight would carry on downwards, but with half the light, which is not the way it works in Minecraft. In Minecraft, the sunlight propagates, I think, propagates all the way downwards until it hits a block, and when it hits a block, it stops. So if it hits a leaf block, it doesn't carry on through the leaf block with less light, it stops at the leaf block, and light propagation takes over from that point. So as far as the sunlight is concerned, underneath a tree is completely black, and the reason you get your shadow is because the blocks around the tree that are under direct sunlight propagate under the leaves. So we're going to keep track of that by having a bool, and the bool is just going to be called obstructed, and it's going to equal false. And then under there, we're going to say for int, we're going to do a loop, for int y equals start y. Y is greater than minus 1, so it's looping from wherever we tell it to start from down to the bottom block of the chunk. And then obviously y minus minus, because we're going downwards, not upwards. And then in here we're just going to cache the voxel because it makes it a bit easier to type. So voxel state, voxel equals chunk data dot map x, y, z. Nice and simple. And now we only have to type voxel. We want to get at the voxel details. So the first check is if we are obstructed, and we don't need to do anything fancy. We're basically just going to set voxel.light to 0. If we're not obstructed, the next check wants to be if we should be obstructed. So if voxel.properties.opacity is greater than 0, so we're not a completely transparent block like glass or air. In that case, we will still want to set voxel light to 0, but we also want to set obstructed to true. And then because we are casting natural light, and there's only really 2 versions of natural light, which is there or not there, if we're not obstructed and we haven't hit a block that has opacity, then we just want to set voxel light to 15. And then we want to do a function, which we're going to put up here, for basically working out a whole chunk. So this one's going to be called public static void recalculate natural light. So yeah, we're calling it recalculate because if you do use it during the game, it will be recalculating all the natural light in a chunk. It basically overrides the existing lighting and starts from scratch. So this is going to take in a chunk data. It doesn't need to take in anything else because we're doing the whole chunk. And then all we're going to do is for int x equals 0, x is less than voxel data dot chunk width x plus plus, and then we'll just copy that for the z. And obviously we don't need to factor in the y value of the chunk because that's what this is doing here. This is going from top to bottom. All this is going to do is call cast natural light, and it's going to pass in the chunk data that we've passed in here, the x value, the z value, and then for the y value, we're just going to pass in voxel data dot chunk height minus 1. And if we just passed in chunk height, we would get this, it would still work, but we would also get this error warning us that we are trying to start from too high. Now to make use of this, we're going to go find our chunk data script, which I think is in here. And under populate here, just before we've done add to modified chunk list, we're just going to say lighting dot recalculate natural light, and we're passing this. So if we run that now, we should find that the lighting is kind of back to normal-ish. Well, I mean, nowhere near back to normal, but you can see we haven't got any tree shadows because we haven't done that part yet. But we have light above and dark below, which is part of the way there. So one thing to note in the subject of saving and things, if we go to voxel data, not voxel data, chunk, sorry, and we go find voxel state. In fact, you know what, let's just quickly do this now. We're going to put this, because this is going to start to get quite busy, this class, so we're just going to yank it out of here, and we're going to put it in its own class. We might as well put it in the data class here, so create a new C# script, call it voxel state, and then just paste this whole amount back in there. Everything should be back to normal now, no errors. Basically, when we save everything that is serializable. So we've serialized this class, which means we can save this class. Bytes are serializable. However, we do not want to store the light value. Now, the reason for this is, one, in the current situation where we have a byte ID and a byte light, it doubles the amount of information that we're storing in what is already going to be quite a lot of information. And then the other thing is we're going to be recalculating the light whenever we draw a chunk anyway, so there's no point in storing a light value because we're just going to be overwriting it. It's a waste of time. So the way we're going to get around that is this one that we need to worry about, because this one isn't really data, this is all access. This one is what we're actually storing, and we want to make it system.non-serialized. And that will mean that when we come to save this voxel state into our chunk, this will not be saved. It's basically, for now, it's just going to be storing the ID. And that's going to be important going forward because we're going to be adding more stuff to this, and none of it we want saving. So let's try and get light propagation up and running. So if we go to chunk data, we're just going to create a queue and a function for adding to that queue. So queue voxel, and this we will get to the point where we make tree shadows work as well, obviously. The queue is going to take voxel states, and it's going to be just called light to propagate. And I will tell you now, this is a temporary queue, so don't worry too much about what you call it or anything. We will be getting rid of this queue before the end of the video. Just thought it'd be easier to show you, to sort of transition from the way we were doing it before to the way we're going to be doing it. This is an intermediary. And then the function is just going to be the same as before, public void add, or same as the chunk update function, sorry, add light for propagation. But because this one is temporary, we're not going to do any checks. We're just going to say voxel state voxel, and then in the function we're just going to add it to the queue. Light to propagate dot unqueue voxel. So what would be nice is if we didn't need to go looking for a voxel anytime we needed to do anything with it. And by that, I mean finding finding the chunk that it's in, and then finding the XYZ coordinate and all that kind of thing. It would be nice if we could just say to the voxel, do this, and it did it itself. So that's exactly what we're going to do. So if we go to voxel state, we're going to create another non-serialized value. We'll put it up here. And this one's going to be a chunk data value, chunk data. And then in our constructor, we're going to take in a chunk data. And the reason we're going to put it here is because there is no situation where we would create a voxel where it is not in a chunk. It needs to have an underscore behind it. And then we want to set this, and we need to, for reasons that might become a bit more clear later on, we need to set this before we set light. So chunk data equals underscore chunk data. And if we go to chunk data itself here, we just add a this at the end there. That should fix that error. Don't think we've got any more references that we need to worry about. Nope. Okay, so that should be that. And then in chunk data, we are going to, no, that's chunk. In chunk data, we're going to create another non-serialized. So this is, again, we don't want to save this. And this one is just going to be a public chunk. Did I actually make that last one public? I did not. This needs to be public. The reason that this one is not part of the constructor is because we can create chunk datas without having a chunk to attach them to. That's the whole point of having chunk data, is that we can create the data without having a chunk there. And then when the chunk comes to need to be drawn, the data's there and waiting for it. So this we're going to set separately by the chunk when the chunk loads it. So if we go up to the top of our chunk script, and just here, after we've set our chunk data, we can say chunk data dot chunk equals this. So above where we actually initialize or set our voxel state, we're going to do a little bit more work here. So we're going to cache the global position of the voxel, because we're going to be doing more stuff that requires it. So it's easier than typing all of this out every time. We'll just call it global pos. That'll do. Equals new vector3. And actually we can just grab all of this, yank that out, put that there, fix this error by putting voxel global pos there. So now a voxel state can access its own chunk data because we're giving it the chunk data there, and then via that it can access, if it's got one, it can access its own chunk, because we have a public chunk reference in our chunk data, which will come in handy later on. So now we're going to do a little bit of validation. If we go to voxel state and we go to light, we're going to expand on our light set. So the first thing we're going to do is say if value does not equal underscore light. And the reason we're doing that is because we're going to be running code for propagating light, and there is absolutely no point in running any code for propagating light if the value hasn't changed. So then if it has changed, we leave our light value, and then we say if underscore light is greater than 1. So if it's bright enough essentially to make anything around it brighter. So if the light value was 1, obviously if it's 0, it's not going to be illuminating anything around it, but light drops at a step of 1 at a time every block you get away from a light source. So the next step down from this block, if it was 1, is 0. So it has to be at least 2 to make a block around it lighter. So if it's greater than 1, chunk data dot add for light propagation this. So now that we've got our voxels to automatically add themselves for propagation, to actually propagate them, we have to check the neighbors, which is a bit of a hassle when we have to go looking for them with XYZ values. So let's make it so that each voxel can store a reference to its own neighbors. And again, this is going to be non-serialized because we don't want this saved in the file. For this, we're going to create an array for storing each neighbor. And this array is going to be in the same order as everything else that we do when we're checking faces. So this face checks array here. What that means is we can use this same array to loop round through the faces, and we know that the 0 neighbor is going to be the, what's that, back neighbor. The 1 index neighbor is going to be the front neighbor, and then the top neighbor and the bottom neighbor, and so on. So back into voxel state, somewhere up here, once again, non-serialized, and it's just going to be a public voxel state array, which we're just going to call neighbors, and it's going to equal new voxel state length of 6. So we're going to have to populate this array, which we're going to do in our chunk data.populate function. So the first thing we want to do is steal the isIfVoxel in chunk bool from our chunk function, and there's no point in having 2, so we can literally steal it, as in take it out of the chunk function and put it in our chunk data function, because the chunk data is what is dealing with the actual data. The chunk, we want to basically keep stripping it down until it is just concerned with the physical presence of the chunk in the world. So the meshes and the textures and all that kind of thing. All the data side of things is going to be handled by chunk data. So head over to chunk, find isVoxel in chunk, and completely rip that out of there, and then go back to chunk data, and down at the bottom somewhere we'll just paste that in, and I think it should just work as it is. And then we'll just create a second one, which is public. Oh, sorry, we do need to make this one public because we're going to need to access it from outside of the chunk. And we'll make a second one, which is voxel in chunk, and this one's going to take in a vector3 int just to give us another option for accessing this particular bool. And all that's going to do is return is voxel in chunk, and then the value it's going to pass in is pos.x, pos.y, and pos.z. And that just allows us to pass in a vector3 int because we're going to be increasingly using vector3 ints, so behind it just be able to pass in the whole thing. And then one last value we're going to put here while I'm here is voxel state, voxel from v3 int. So this allows us to pass in a vector3 int, and it will return the voxel state of that vector3 int. So return map pos.x, pos.y, pos.z, and this is obviously a local vector3 int, so the global one won't work for this. It needs to be the 0 to 16, 0 to 128, I can't remember how high the chunks are, but that value, not the global value. And if we just jump back into chunk, I believe we should have some errors. Let's get rid of that search, and we can fix these by just saying chunk data before that. And they should just work the same way they did before. So back into chunk data, after we've created our new voxel, so down here, we want to loop through each of the neighbors. So for int p equals 0, p is less than 6, p++, and then vector3 int neighbor v3 equals new vector3 int, and we're going to pass in the x, the y, and the z, and then plus voxel data dot face checks using the p index. And we'll say if is voxel in chunk, and we'll pass in the neighbor v3. Much easier than typing in the xyz. If it's in the chunk, then we're just going to say map xyz dot neighbors index p equals voxel from v3 int, and then we're just going to pass in the neighbor v3. However, if it's outside of the chunk, we're going to say map xyz dot neighbors p equals world dot instance dot world data dot get voxel voxel global pos plus voxel data dot face checks, and then once again the p index. So you may be wondering, what if the neighbor has not been set? So if you see that we're looping through here from 0 to chunk height and 0 to chunk width and 0 to chunk width, if a voxel is setting its neighbors, it's going to have all the neighbors to the left, bottom, and back of it, and none of the neighbors to the front, top, and right of it. Basically, that's going to mean that half the neighbors, all the neighbors to one side, or three sides, are not going to be there. Well, setting a null neighbor isn't a problem at the minute because we're not doing anything with it, but we do want to fix that problem. So what we're going to do with that is we're going to create a reverse lookup array. So right now we have all these, but there is a counterpart to it. So like this one is, what is it, back, and this one is front. Say we have one voxel and we look up the front face of that voxel. We know that the adjacent face of the voxel next to it is the front face. So the back of one voxel meets the front of another voxel. So we're going to create a lookup array that uses the same order, the same winding order as this, but gives an opposite index. I hope that made sense. So public static read only int array. We'll just call it rev face check index. It's going to equal a new int of 6, 1, 0. I've worked these out in advance, obviously. 3, 2, 5, 4. So as you can see, if we call on number 0, the returned index is 1. So basically, if we are looking at the back face of one voxel, then we know that the neighbor of it is the front face of the neighboring voxel, and we can use this to set the neighbors. So what we're going to do is when we set a neighbor, we're going to check the opposite neighbor to see if that is null. If it's null, we can use this to set the neighbor's neighbor to the current voxel. I'm going to be saying neighbor's neighbor a lot, but before we do that, there's a little bit more code we need to write. So let's just, before I forget, we go to voxel state. There is another light value I want to create, and this one's going to be called public byte cast light. So this is going to dynamically work out how much light our voxel is giving off, taking into account opacity and light fall off. So int light level equals underscore light minus properties dot opacity -1. Now, the reason that we cast it as an int is because bytes wrap around. If you subtract 2 from a byte that is at level that is currently set to 1, then it will go all the way around to 255. And obviously we don't want that, because that means that if a voxel has become completely dark, it will flip all the way around to as bright as can be, which is obviously not what we want. So we want to set it as an int first so that we can run a check on it. Say light level, if light level is less than 0, then light level equals 0, because if that was a byte, then it would never be less than 0. That would return false, because if it had got less than 0, it would have flipped round to 255. And then we can simply return, we need to recast it as a byte, for byte, light level. So that gives us the amount of light that this voxel is reflecting outwards. This is natural light, not block light, so this isn't a light source as such, but this is the amount of light that is coming from this block. So any block next to it that is darker than this value needs to be set to this value. And then we're going to create another function, which is going to be called public void propagate light. And this is how it's going to propagate itself. So chunk data dot chunk dot add for, oh sorry, not chunk, just chunk data, add for light propagation, and we're adding this. So if we go back to light propagation, we can now add some propagate light code. Public static void propagate light voxel state voxel it will take in. Starting to talk like Yoda when I'm coding. It's never a good sign. So the first thing we want to do is just do a little check just in case if we happen to have somehow handed in a voxel that is null, or we've handed in a voxel that has a light level of less than 2, then we don't need to do any propagation because it can't cast any light. So if that's the case, just return. So next thing we want to say for int p equals 0, p is less than 6, p plus plus, and this is just, as always, to loop through all the neighboring faces or all the neighboring voxels of this current voxel. Then we want to say if voxel dot neighbors p does not equal null. I'll just post this bit of comment in here. This is important. We can only propagate light in one direction. So if we sort of said, if the light is lower, propagate light. If the light is darker, propagate dark. So if we did it both ways, we end up with a recursive loop where it just keeps going backwards and forwards. So we only ever go in one direction. Only light propagates. We don't propagate dark. I'll show you how we handle dark in a second. If voxel.neighbors p dot light is less than voxel dot cast light, so if it's less than the amount of light that our voxel is putting out, then we just set it to equal voxel dot cast light, and that is basically all there is to the propagation code. So right, okay, sorry about this. I've been putting this video together in pieces over the last 2.5 weeks, and my notes are a little bit jumbled up, so I'm just gonna try and make the best of it as I can at the minute. So this propagate light code, we're just going to steal it completely out of here, delete that function, and into voxel state, we're going to replace this with that. And this will make more sense as we go along. So in our propagate light, we are directly calling the propagate light code. We don't need this check at the top, obviously, because we're in the voxel. So we know that the voxel is, or we don't need this part of the check. We could still do with the light check here. So we'll just delete the voxel part. And again, delete all these. There, so this handles its own propagate light, and for reasons that will become clearer soon, we are also going to go to chunk data and we're going to get rid of this because we're not going to be using it. I was going to go through the method of adding it to that and then sort of transitioning from that to the way that we're going to do it, but my notes are so jumbled up that I'm just going to make a mess of it, so we're just going to go straight to the way that I'm going to do it. So the first thing we want to do is we want to sort that neighbors script out. So what we're going to do with the neighbors is we're going to create a custom class to handle the neighbors as an array, but one array that we can validate. So create public class voxel neighbors, which we'll try and spell neighbors correctly, at least correctly for where I'm from. And then in here, it's going to take in a public read-only voxel state parent. And the read-only part means that it can be set in the constructor for this, and that's the only time you can set it. And then a public voxel neighbors constructor. Voxel neighbors constructor. It's going to take in a voxel state, which is going to be, we'll just call it underscore parent. And then all it's going to do is set the parent equals underscore parent. So we need to create an actual array to store our voxel states, and that's going to be private. It's going to call it underscore neighbors, and it's going to equal a new voxel state And we know it's 6 because there's only 6 faces to a cube. And then we want a public int length. And this is obviously the length of the array. Return neighbors.length. We could also just return 6. We know how long it's going to be, but let's just leave it as that. And then finally, the way we actually access this array is public voxel state this, and then we pass in an index, and then we do basically a get set, just like we did with other regular values, only now it's an array and we can pass in an index. Return underscore neighbors index. And that just pulls out the index that we pass in, that just pulls it out of the array as it would normally do. But the bit that is interesting to us, or the bit that is useful to us, is that we can also set it. So we pass in the index and we say equals value, and that allows us to actually run validation on our neighbors when we set them, which is what we really need this for. So the first thing we need to do is go to our voxel state up here. That's just going to be a call to Propagate Light. So our neighbors array here, we're going to replace with a voxel neighbors. And the class itself is an array, so we don't need to tell it it's an array. And it's just going to equal a new voxel neighbors, and we pass in this voxel state as a parent. Or do we? Oh, sorry, no, we can't initialize it here. We have to initialize it in the constructor. So if we go down to the constructor, which is here, just after we've initialized chunk data, we're going to say neighbors equals new voxel neighbors this. And another thing that we're going to be using, and we need to create another non-serialized value for, is the position of this voxel. And again, we don't want to store this. Public vector3 int position, and then we'll pass that in here. Again, there is not going to be a voxel generated or created that doesn't have a position and a chunk and an ID. Vector3 int underscore position, and then we will set that. We just need light to be last. It doesn't really matter about the rest of the order. So position equals underscore position, and then we're going to create another little function that allows us to get the global position of this voxel. We'll just put that there, and it's going to be a public vector3 int global position. It's just going to be a get value, return new vector3 int position.x plus chunk data.position.x. Position.y is just position.y. If you are doing multiple chunks high, like stacking chunks, then obviously you'll need to factor that in when you do your code. And then position.z plus chunk data.position.z, or y, because that's a vector 2, sorry. So that just gives us a way of getting the global position of our voxel without storing any additional data other than the local position and the chunk data. So once again, we should have an error in chunk data, which we just fixed by passing in a new vector3 int x, y, z, and that's the local position. That's why we're not using this one, because that needs to be the local position. So for actually setting those neighbors, we're going to create a little function for reciprocating when we add a new neighbor, which is going to go in the voxel neighbors class. And this will basically check a neighbor to see if the voxel set is this neighbor, and if it's not, it will set it. And this way, any gaps that get left behind, because we're working from left to right and from bottom to top, or top to bottom, whichever way around it is, any that get left behind will get set when the neighboring voxel checks the other side. So if we go back to voxel state and we go down to our voxel neighbor class, and down here we will create a function. Doesn't need to be public. Return neighbor. It's just going to take in an index, and this is the index, you know, the 1 to 6 or the 0 to 5 index that we use for checking faces and things. And the first thing we want to do is if neighbors index is equal to null, just return, because we can't check to see if the neighbor has the correctly set its neighbor if that neighbor doesn't exist. And there will be times when the neighbor doesn't exist. So another big block of comment here, just to make clear what's going on. This is another situation where we can end up with a recursive loop if we don't do it correctly. What we're going to say here is if underscore neighbors index dot neighbors, and then to get the index of the neighbor's neighbor that we're looking at, we go voxel data dot rev face check index, and then pass in the index. So bearing in mind that's getting us the index in here that we want to look at to get the opposite neighbor of the one we're actually checking. I really hope that makes sense. It's not easy to explain. If that does not equal parent, which is the voxel that this voxel neighbors array is part of, then we want to make sure that it does equal parent. So now we can put some validation code in our neighbors get set. Not set, sorry, get. We don't want to do it in a set. We're only doing it in get. So if underscore neighbors index is equal to null, then the first thing we want to do is try and get it from our get voxel thing. So if neighbors index equals, don't forget to close your brackets, equals world.instance.worldData.getVoxel, and then we want the parent.global position plus voxel data.faceChecks index. So we're passing in the neighbor of this voxel, and we're asking world.data.getWorld to find it. It's going to return something. It might return null, but either way, it will return something. And then we can call return neighbor, and we pass in index, and we spell return neighbor correctly. And then finally, we return whatever is there. It could be null, but either way, we're going to return it. And then in set, we want to do the exact same check. Well, not the exact same check, but we want to run return neighbor again. So we just say return neighbor index just to cover all of our bases. And now what we can also do as like an additional check is if we go into chunk and we go down to update mesh data. Yep. We can get rid of this commented out line of code there. Where we do a check for the neighbor, which is here, we can replace this check voxel code with chunk data.map xyz.neighbors p. And then what that will do is that if somehow we've got to this point and that neighbor has not been set, this will set the neighbor before we actually do any drawing of chunks. So I can't think of a situation where we would get here and the neighbor's not being set, but if it happens, we will set the neighbor here. The only reason it wouldn't be set is if the neighbor doesn't exist, say the chunk's at the edge of the load distance or the end of the world or something like that. And also this renders check voxel here completely useless because that's the only time we're using it. So we'll just get rid of that. So it's time to get a little bit freaky in our voxel state light value. We're going to make this a whole lot more complicated. So just because we're going to be writing so much of it, I'm just going to delete the whole set part and we're going to start over because there's going to be a lot of stuff going on. So well, I didn't need to delete that first bit because that bit stays. If value does not equal light underscore light, then we do the stuff that we're going to do. There is no point in doing any of this if the light value is the same. So the first thing we're going to do is cache the old light and cast light values before updating them. Byte old light value equals underscore light, and then byte old cast value equals cast light. So once we've done that, we can then set the light value, which is, so we're just going to say underscore light equals value. And I'll try and paste these comments that I made in my own code here. I know my code is getting extremely over commented in recent videos, but the whole point of the videos is so that you can learn how to do what we're doing. So it's not meant to be functional code. It's meant to be educational code. So the first thing we're going to check is if underscore light is less than the old light value. So that means that we have made our voxel darker. Now, if we've made it lighter, things get a little bit easier because all we need to do is propagate the light, basically. We'll do that now because it's easy. If it's darker, then we do whatever we're going to put in there. If it's lighter, we say else if, and we need to do a check here. Else if underscore light is greater than 1, because obviously there's no point in trying to run this propagation code if it's darker. Propagate light. However, if it's darker, we've got quite a bit to take care of. So the first thing we're going to do is create a little list of ints, which we're going to call neighbors to darken, and it's going to equal, do you know what? It can just be a q int neighbors to darken, going to equal a new queue of ints. And then we need to loop through each of our faces like we've done a million times. Int p equals 0, p is less than 6, p plus plus. The disadvantages of typing without looking at the screen. So our first check is if neighbors p does not equal null. This is another section where things can go real bad if you don't do things correctly. So first thing we're going to do is make sure we have a neighbor before trying to do anything with it. So that's what this check is for. And then the next thing we're going to do, if a neighbor is less than or equal to our old light value, it means that this voxel could have been lighting it up. It might not have been lighting it up, but it definitely could have been. So basically what we want to do is set it to 0, and then it's going to run its own light checks, and it'll check all its neighbors. And as you'll see in a second, if a neighbor is brighter, it will tell that neighbor to propagate, and then that neighbor will do its neighbor checks, and it'll see this one is darker, and it will raise its light value. So that's the way it works. So if neighbors is less than or equal to old cast light value, then neighbors to darken dot on queue, and we're just gonna, it's just the index value that we're adding. Of course, that needs a semicolon on the end. And then the next part is, if the neighbor is brighter than our old value, then that voxel's been lit from somewhere else, as I just mentioned. Then we tell that voxel to propagate, and then it will check its neighbors. It will see that this voxel is now 0 or darker, and it will propagate itself. So neighbors p dot propagate light, and then that neighbor will do its own propagation, which is this bit down here. It will do that by itself. So once we've got through all that, we get to the end of the loop, while neighbors to darken dot count is greater than 0, and then we're just going to say neighbors, and then we get the index from neighbors to darken on queue, no sorry, DQ, not on queue, dot light equals 0. So we're setting voxels around us to a darker value, or to 0 value, and then light will propagate to them to get them back up to whatever light level they should be at. And then we're going to say if this voxel is part of an active chunk, so we do need to check that there is a chunk attached to it, because lighting can be updated on chunk data where there is no chunk. So if chunk data dot chunk does not equal null, then world dot instance dot add chunk to update chunk data dot chunk. And because we've done this check here where we make sure that we're not adding a chunk that is already in the list, then that means we don't need to worry about adding 58 versions of the same chunk. And there's a couple of changes that I've just remembered we need to make. There's a possibility we can get a Stack Overflow error. So if we go into world data, get voxel, that's voxel data. I don't have world data open. Just ignore any errors for now. We're only halfway through the code. No, we don't have any. Pleasant surprise. Go to data, world data. And then if we go down to get voxel, right now we've got this set to request a chunk if we don't have one. We don't want that to happen because that could cause Stack Overflow errors. So we're going to say false, and then we're going to say if, at this point, if chunk is equal to null, return null, rather than trying to return a voxel. I mean, we're doing checks to make sure voxels are null, so if we ask for a chunk, we ask for a voxel and that voxel it does not exist, then we can just return null, it's fine. So the next step is we are going to add a way of modifying voxels that takes everything into account. So if we go into, I think chunk data, yes, chunk data, and we're going to create a new function, and we'll put it here. This one's going to be public void, and we're going to call it modify voxel. And it's going to take in a vector3 int pos and a byte ID. And the first thing we're going to do is, if we have somehow tried to modify a voxel to be the same voxel it already is, then we may as well just return. There's no point in messing around with it. So in that case, map pos.x, pos.y, pos.z, .id is equal to underscore ID, then just return. Sorry, this should be underscore ID. Next, we're going to cache the voxels just to make it a little bit easier. So voxel state voxel equals map pos.x, pos.y, pos.z. And then the other one is going to be just a block type because this is a hypothetical voxel. This voxel doesn't exist yet. So block type new voxel equals, if you remember I said we can't create a voxel without having a chunk to put it in and giving it an ID and stuff. Well, this isn't a real voxel, so we're just going to get the block type that gives us access to all the properties, which is the only bit that we need. And that's going to be world dot instance dot block types, and then we just want to give it the ID value. So that gives us the properties of the potential new voxel that we are, well, the voxel that we are changing it to. So the next thing, cache the old opacity value, because if the opacity value hasn't changed, then the lighting isn't going to be changed. That will be different when we add block lighting at a later date, but for natural lighting, the only thing that can affect the lighting or make the lighting change is if the opacity has changed. So byte old opacity equals dot opacity. Then we can set the new voxel, and it's going to be voxel.id equals underscore ID. And the next part is if the opacity values of the voxel have changed and the voxel above is in direct sunlight, or it's the very top voxel of the chunk, then we want to recast light using our lighting.recast function, or lighting cast natural light function from this point downwards to update all the blocks below it. Remember, none of the blocks above it will be affected by this change. That's different for block light, but for natural light, it always goes downwards. So if voxel.properties.opacity does not equal old opacity, and I'll stick this on a new line because it's easier to read and stick it in brackets, and pos.y is equal to voxel data.chunk height -1, or, sorry, misspelled voxel there. Such a complicated word. Or map pos.x by pos.y by pos.z dot light, sorry, the pos y wants to be +1 because we're looking at the block above the one that we're changing. Dot light is equal to 15, and it needs to be 15. If it's not 15, then it's not in direct sunlight, and we're only interested if it's in direct sunlight. If that's the case, then lighting dot cast natural light, and we're passing in this chunk data, pos.x, pos.z, and then we're starting from the one above where we are, pos.y +1. And we need to, when we do this check here, we need to check this one first to make sure that it is below the voxel chunk height level. Because if we just did this and it was the very top voxel of the chunk, we would get an error saying because that's outside of the world. So first we check to see if it is the top voxel, and if it's not, then we say is the one above it in direct sunlight. And then because we've modified a voxel, we want to add this chunk data to the modified chunks list. World.instance.worldData.add to modified chunks list. And then if we have a chunk attached to it, we want to add that chunk for updating. So if we have a chunk attached, add that for updating. So first we check to make sure the chunk is not null, and then we say world.instance.add chunk to update chunk. So now we want to make use of this. So the first place that we're going to make use of it is in, I think, set voxel, world data set voxel. In set voxel, where we actually set the voxel here, we can just delete these two lines because we're adding to the modified chunk list in the function that we're about to call. So we say chunk dot modify voxel. The position is the voxel there, that value, and the ID is obviously the value, and that automatically, everything is funneling through this at the minute, all our voxel modifications and all that, so we don't need to go change any of that. But what we do need to change is in chunk we have our edit voxel function, and that is going to have to be updated. So edit voxel, there we are. Right, so we no longer need this. Well, first off, we don't need this add chunk to update because that's taken care of in the modified chunk, and we don't need the lock because that's taken care of as well. We don't need the add to modified chunk because that's taken care of. So basically all of that can go away, and then we're just going to say chunk data modify voxel, and then we'll pass in a new vector3 int, and it's going to be x check, y check, z check. And then the value is obviously new ID. And we don't need to change this. This is just adding neighboring chunks to the update list. Just a little bit of cleanup now, and I think we're more or less done. So if we go down to Propagate Light, we want to do the same chunk add update thing that we just did in Modify Voxel. So I'll say if chunk data.chunk does not equal null, and let's try and spell chunk data correctly, then world.instance dot add chunk to update chunk data dot chunk. So if we propagate light, then we know we're going to be updating this chunk. And again, because the add to update function automatically checks to make sure that the chunk isn't already in there, we don't need to worry about that. We are going to make one other change. I just remembered, or I didn't remember, I just saw in my notes that I actually, here where we used a, where is it? Yeah, we used a queue. We actually used a list for a reason the first time I did it, because the queue, it doesn't cause an endless loop. It doesn't freeze up the system, but it does make it a lot slower. And as you're going to see, we're already going to have some performance issues with this system. And fair warning, ones that we're not going to fix today. But yeah, so list, not queue. And then down here, this wants to be add, not unqueue. And then down here, this is going to be a for loop. So for each int I in neighbors to darken, and then we just pass I into there. Let's give it a go and see what happens. Okay, we have tree shadows, we have no weird cross chunk lighting things, and if I find, let's just zoom in on our player here, if I switch to underneath and switch to orthographic, let's get him under and above a nice little cave. Now, I want it to be a little cave because I'm going to have to show you some performance issues we've got. Just a quick note, this weird, I don't know if you can see it in the video, but there's a weird freezing thing that happens. It's kind of like a lag spike. It's not related to the code as best I can tell. It's something to do with the editor because one, it doesn't always do it. Like sometimes I'll open the editor and it doesn't do it at all. Two, it doesn't do it in the build. If I build the game out, it doesn't do it. And three, if I open the profiler and check, it's actually the editor loop that's causing the lag spike. So I'm not sure what that is. Maybe a different version of Unity wouldn't have this problem, but yeah, I've not really anything I can do about it. So if I now dig down, now I've picked this small cave because there's a performance thing I'm going to have to show you. So as you can see, it's worked. So I've just dug this bit of cave out here so you can see it in action. It's a bit darker over there, obviously. And if I block this off, everything's dark again. Now you may have noticed, it might be hard to tell in the video, that there is a bit of a lag when I block things off. That is an optimization thing that I haven't figured out yet. I really wanted to get this video done so you can see the cross-chunk lighting in action. But yeah, it's not the most performant. So we've got to figure out how we're going to proceed with threading. Are we going to make this system thread safe, or are we going to try and use the Unity job system? And we need to optimize this because if this was a bigger cave, we'd be waiting a good 5 seconds for this to propagate. But yeah, this is already a stupidly long video. It's been a long time coming. We finally got cross-chunk lighting working. I can finally move on to some other things, but there will be, basically I've got some smaller videos planned to cover a few little bits and bats that don't really warrant a full video of their own, but aren't quite appropriate to be stuffing in with other videos. And like some of them, like the fixing lighting performance, obviously would be fine in this video if it weren't for the fact that it's already going to be over an hour long. So yeah, that basically is it. So all that's left to do now is to thank my amazing Patreons. Everybody, whether you're just liking, sharing, subscribing, all that, that's great. And everybody who's a Patreon at any tier, thank you very much. For the people who are on the special Sugar Daddy / Mama level who are donating at the top tier, they get special thanks. So they are, as always, Professor DJ. His Cola project is coming along nicely. By the way, any of your other top Patreons, if you've got a project you want me to shout out, let me know. I may have to rethink it if I get a lot of Patreons at this level, but at the minute it's a nice manageable number, so I don't mind giving shout outs to projects for you guys. Professor DJ's got his Cola project where he's making his own programming language. It's coming along nicely, and he seems to be getting quite a lot of traction on that, so go check that out. You can find details about that in the Discord. Reg Reed, Michael Gulak, Gabriel White, and Dave Maldine, you guys are amazing. Thank you very much. And we will be back soon. I've got a details of a live stream coming up because apparently that's something you guys want, despite the way this video has gone. And I'm hoping to get quite a few videos out in a much shorter amount of time in the coming weeks. Some of them are going to be shorter videos, some of them are going to be different videos. Basically, my whole occupational landscape has changed recently, and I'm looking to make YouTube a bigger part of that now. So you can expect more content. Hopefully it's content you want. And that's it for now. Thank you, everybody. We'll see you next time. Bye-bye.